Welcome, everybody. All right, today must be a beautiful day out because at least 1/3 of the seats are empty. Okay, one quick announcement. So, project, which one? Where are we now? 3. A knife base will hopefully be shipped tonight or tomorrow. Yep. Also, there will be next week will be 3 really cool machine learning talks here at Cornell. For those who are interested, we had one last week, 2 weeks ago on computer vision, which was really, really fun on deep learning. I saw some of you went. Next week we have one on robotics and machine learning, one on healthcare machine learning, and one on machine learning, core machine learning. I will announce it on Piazza, but if you want to see cutting edge research, these are really, really cool talks to attend. All right, one quick thing. So one thing I actually didn't get around to yet is project 1. So that's now done. And I just want to say we have, it's really, really fun to see the leaderboard, people moving up on the leaderboard. So maybe, I want to spend maybe 1 minute looking at the top results. So Steve Nash and Carl Sagan, can you repeat yourself? Where is the team Steve Nash and Carl Sagan? Can you raise your hands? Okay, can you tell us, please be quiet, guys. Can you please tell us what you did? What was your secret sauce? Okay, and how did, so for everybody else, so they did feature weighting. So when you compute the distance, you weighted each feature differently. How did you find the weights?
So the first thing we did was for facial recognition, we tried to black out the corners and emphasize the center more, but that didn't actually work. So then we tried different random functions for the coordinate systems, the bell curve, and then so for handwritten digits, it turned out that the bell curve was good.
Oh, interesting, okay.
And for the facial recognition data, it was like just a straight up implicit function with the index of the textbook file.
Oh wow, okay, interesting. So what they did is basically they computed weights for every single feature and they used different functions for different data sets. So they tried out basically, for example, a Gaussian weighting, so that would weight points in the middle, or x plus y, I guess, weights the bottom right corner though.
Well, yeah, it was interesting though. For some reason when you weight it's not exactly x plus y, but it's because it's all 1D, right? You just make it 1D, right?
Oh, I see in that one, okay. Interesting. So there's a whole industry in metric learning. So the way you make k-nearest neighbors truly competitive is actually by learning metrics. So that's basically, you the guys took the first step into that direction, right? Where you basically, the idea is during training you actually given some data and now you actually want to learn a metric such that during testing a k-nearest neighbor classifier would do really, really well. And that is essentially actually how, for example, Facebook does face recognition. Right, so they actually have some very fancy way of computing metrics of faces. And so then they basically say if you upload an image and they first detect faces and then the question is, who is that person? Well, they now look at, basically do a nearest neighbor classifier with this really, really fancy metric that actually is optimized for faces. And so one advantage they have is because people upload their profile pictures, they have many, many, many faces, and they also know who they are because usually you upload a profile picture of yourself. Not everybody does, but almost always it is. So they have a lot of training data for this. Okay, but how about number 2? That's the witty kitty. Witty kitty. Can you raise your hands? Are you here? All right, they're celebrating outside, not bad. How about Team Garma? It's actually very close on the top. Team Garma's not here either. Oh no, here we go. Oh yeah, Team Garma. What did you guys do? So you speak up a little, yeah.
I heavily optimized the Julia code so that I could run very quickly, and then I basically translated images in various directions, and then added all the data points.
Oh, interesting. Oh, wow, interesting. Okay, cool. That's called data augmentation. So that's actually interesting because these are completely orthogonal approaches. So you can combine them, and then you would actually, if you joined your teams, you would have beat everybody. So just one more time, what he's doing is he basically takes the training data and he modifies the training samples ever so slightly such that basically the sample does not, the label does not change, right? So for example, let's say you have a digit of a 6, right? If you just take this image and just move it a little bit to the right, a little bit to the left, it's still an image of a 6, right? Is that correct? And so the advantage of this is you get a lot more training data, right? And so if your test image maybe is a little bit to the right or a little bit to the left, then actually you have a better chance of actually finding out the neighbor, right? And this is actually a trick that people use in practice a lot, right? It's called data augmentation. So when people actually, for example, they do exactly this, by the way. They take images and move them a little bit. They rotate them a little bit. They flip them. You can't do this with everything, right? But with people, you can flip them, right? And they should still be, faces, etc. And this way, you basically artificially increase your training data set. It's a very good approach. Awesome. This is very, very nice. I love that you guys actually basically got to the top by actually, adding totally reasonable things to the classifiers. Okay, good. So I handed out a little handout. Who did not get the handout? Raise your hands. Everybody got them? One person. Okay. Who has two? Okay, good. We resolved the problem. So this is a very quick little quiz. It's not meant to be hard. It's actually from an undergrad class, an entry-level undergrad class. But it's on naive base. So why don't you and your favorite neighbor go through this and just try to figure it out. One thing is, just to clarify, the last question, I really want you to use naive Bayes, right? So earlier on when it says CPT, CPT means conditional probability table. That basically means, what if I estimate the probability just given this table? Later on, if I make a prediction, that means, what if I use the naive Bayes algorithm? So please discuss it with your neighbor and just go through it.
Quick question.
Yeah.
A quick.
Maybe actually it's, well, let me just, okay, so question 7. So Susie goes on a date, and anyway, there's a horribly bizarre story, but what's the prior probability that the person is good? Who can tell me the answer? Come on, this is the easiest one. Yeah, 1/2, right? So the first one is 1/2. Why is it 1/2? Because you just look at y, and without any other knowledge, right? Well, 50% time, half the people are good, half the people are bad, right? So she has a, just estimating p of y from the data is just gives you 1/2 probability. All right, so then she wants to train a naive Bayes classifier, and for this she constructed CPT, so CPT is a conditional probability table. So that basically says, what's the probability of this random variable given this random variable? So the first entry is, what's the probability of not C, so the person is not wearing a cape, given that the person is good? Who can tell me? Yeah?
1/3.
It's 1/3. Why is it 1/3?
Well, first you would eliminate anything where it's not y, and then you would look at just those that have y, and you see how many are not.
That's exactly right, right? So you basically say, out of those people, like, you throw away everybody who's not good, where y is false, and then out of those where y is positive, 1 out of 3 actually does not wear a cape, right? So it's 1/3. Next one is the probability that the person is not wearing a mask, given that he is good. What's the answer here? Yeah, 1/3 again, right? So this is exactly the same scenario. Then question 10, what is the value of probability P of the person is not wearing a cape, given that the person is good, if you do +1 smooth it? Can anyone tell me? Yeah. 2 or 5, right? So that's basically what you're doing is you say, well, only one of them actually does not wear a cape, but I'm adding 1 to this, so that's where the 2 comes from, right? So I have 1 + 1 over 3 in total, plus 1 that I added in the positive case and 1 in the negative case, right? So that's 2 over 5. So here you're adding 1 for each class, right? So this basically you add 1 heads, and here you add a heads and a tail, right? Can you raise your hand if you got that result correct? All right, okay. So now, next question, Susie spots her date, but to her disappointment, he already sits at the table. She cannot observe his underwear situation. What's the distribution that the person wears his underpants outside his pants? P of U, yeah? Oh, I see. So this here is the total number of tosses. In this case, you basically have coin tosses, where basically you either get a person with a cape or you don't get one with a cape, right? So we're adding, plus one smoothing means you add two tosses, one with a cape and one without a cape. So here you're counting the people without a cape, right? That increased by 1. And the total number of tosses increased by 2. Because you added one without a cape and one with a cape, right? Does that make sense? Yeah. So you basically have to add one per class, right? Okay, what's P of U? Who's brave? Wait, there should be really... Yeah.
A third?
It's a third, right? Yeah, P of U is a third. Okay, good. Sorry, for a second I was like, did I miss something? This is really hard. No, this is just, just 2 out of 6 are true, right? And so, is that true about Spider-Man? I guess, I don't know. Okay, whatever. All right, now comes the last one. So now she actually does her inference, right? She sits down with this guy and turns out he does not wear a cape, he does not wear a mask, because that's, So what's the probability that the person is good given that he does not wear a cape and he does not wear a mask? So who thinks he or she has the answer? Yeah? 1/9? No? Yeah? No? Close, you're getting closer. No? 100%? Wow, you guys are all over the place. No? No? All right, let's work through it. Okay. Well, let me do it here. Let me do it here then. Yeah. So probability of y given not... Can you read this in the back? Raise your hand if you can read this. Okay, good. Comma, not mask, right? So this we can't really observe, right? If you realize this is exactly the dilemma we ran into. This is why we did naive Bayes in the first time, right? In the first place, right? If you look at the table, you actually never see this, right? And so, you want to basically make use of the naive Bayes assumption. So here's what you do. You flip it around. You say, what's the probability of the data that I observe, not C, not M given Y, times the probability of Y over the probability of not C, not M. Okay? So far, so good. Who has it so far? Raise your hand. All right, all right. Now, here on the top, we can use the naive Bayes assumption, right? And instead of this term here, what we do is we write, this is the product over, well, no, let me just write it out. This is P of not C given Y times P of not M given Y times P of Y. Okay, so that's the naive Bayes assumption, that these two, like given Y, these two are independent. So now this factors. Who has it so far? Raise your hand. All right, okay, good. Now comes the second part. Down here we have this guy, right? Well, how can we actually apply naive Bayes here, right? We also have to apply the naive Bayes assumption. And so what we do is we just say, well, this is given, given y prime, and we sum over y prime. Right? So now actually times the probability of y prime. So now this term here factors again. Okay, does that make sense? That this is exactly the same as what we had before? You just basically, look at both cases. Either you have y well, let me write this out. What we basically get is P of not C given Y, P of not M given Y, P of Y, plus P of not C given not Y, P of not M given not Y, probability of not Y. Yeah? Oh, okay. Yeah, let me just write this down one more time then. No, Y prime is just... Okay, let me write this one more time. So what you're saying is basically that P of Y given not C not M equals P of not C not M given Y, P of Y divided by P of not C given not P of not C not M, right? And what is P of not C not M? Equals P of not C not M given Y plus P of not C not M given not Y. P of not Y. Okay, so that's the same thing, right? Does that make sense? And now we've got everything in these nice little conditional terms, and now we can apply the naive Bayes assumption, right? So now this here becomes just the product of two terms. Raise your hand if that makes sense. Okay, awesome. And then you plug everything in. So, all right, so we can now do this. This is like times P of not C given Y, P of not M given Y, P of not C given Y, not M given Y, P of Y, plus P of not C given not Y, of not M given not Y, times P of not Y. Okay. Now the first thing you do is you realize that that's P of Y is always the same, so you can just knock it out, right? You don't need it. That's always 1/2. So you can add it in, but it doesn't really make any difference. And so P of not C given Y, P of not M given Y, well, that's exactly what I let you compute early on. Right? This is exactly the answer to question 7 and question 8 and question 9. So that's basically 1/3 times 1/3. Down here you have exactly the same. You have 1/3 times 1/3. And then what about this guy? Can anyone tell me what this is? What's P of not C given not Y? It's 2/3, right? So 2/3 times 2/3, and that gives you 1/5, right? So 1/5. Any questions? Yeah.
Example highlight the crucial weakness of a naive Bayes classifier in that Susie has constructed a training set that is descriptive but is not necessarily limited pool of blind gay people. So she doesn't know if the actual pool she's drawing from is actually half good guys and half bad guys. But she's going to be working on that prior.
Right. So the question is the following. Well, this data set is nice, right? But, actually it was Susie's mom who created the data set, actually. It wasn't Susie. But anyway, as we're being precise. And so you're right? So, if you go on a real date, well, it's very rare that you're going to date with Spider-Man, right? Usually he's a pretty busy guy, right? So it's not representative. So that's actually not a crucial weakness of naive Bayes. It's a crucial weakness of machine learning in general, right? So you assume that the training data is from the same distribution as your testing data, right? So in this case, if she's not dating any superheroes, then it probably wouldn't apply, right? You would have too different of a distribution. Does that answer your question? Okay, any more questions? All right. Okay, so let me continue then with naive Bayes. Where's my talk? And at the end of last lecture, someone asked me a few people asked me some good questions. So one question was, so we make this naive Bayes assumption, right? The naive Bayes assumption basically says that we can, that these features are independent, conditioned on the label. And the first question someone asked, well, what if that assumption actually holds, right? What if that's true? Is then naive Bayes a perfect classifier? What do you think? So if the assumption actually holds, do you get the optimal Bayes classifier? Or do you not? Let's have a vote. How about this? Vote if yes now. Who thinks yes? Who thinks no? Oh, we have low participation here. The answer is yes, right? So if your assumption actually holds, but we haven't done any fudging since that assumption, right? The assumption was the one fishy thing that we did. Everything else is just, absolutely accurate, right? So if your assumption holds, then you actually recover the Bayes optimal classifier, right? So then it's actually very, very good. So one thing, someone asked me, like, well, when does this assumption not hold? Or can you give you some examples where this is really bad, right? And I thought about one thing. One question was also by decomposing P of x given y into P of x alpha given y, right? Do we overestimate or do we underestimate this probability? And it turns out you really can't say that in general, right? So it could go either way, right? Sometimes probability may be larger, and sometimes the probability may be lower. Can anyone come up with an example where this here is larger than that? And can anyone come up with an example where this here is lower than that? So maybe I give you a minute to discuss it with your neighbor. I think this is very helpful, just for you guys to get some kind of intuitions about this algorithm. So come up with some practical example where you say, by decomposing this, I actually get a larger value than this. So I overestimate the probability. Or think of some example where you underestimate it. Who wants to volunteer an example? Here we have someone brave, yes? Probability, oh gosh, okay, I don't know anything about poker. Okay, probability that you have a full house given that you have 3 kings. But isn't that a full house already?
Yeah, so that's one. On the other side, you have the probability of having a full house giving you 3 kings.
Oh, I see. The features are you have 3 kings and you have. Oh, I see. Okay. So you have 2 features. One is do you have 3 kings? Do you have 2 queens? And you say if both these are the case, then you always have a full house. That's your label. The label is do you have a full house? Yes or no. So okay, good. So if both of these are the case, then actually it turns out you always have a full house, right? But actually, if you decompose it, then actually, sometimes when you have 3 kings, you have a full house, and sometimes you do not, right? So you actually, okay, good. I like this example. That's good. Any other example? Yeah.
If we take the example of the handwritten digit and we assume that pixels are independent, then we would have the probability of having a 6, for example, would be way lower than the normal probability because you're counting on every pixel as independent. Like you're not counting the dependence between the pixels.
Oh, so in terms of handwritten digits, you say the different pixels are not independent. That's right.
Yes. So if we assume that they are independent, then we'll end up with very low probabilities for 6 or for 5, because we consider that every pixel it has independent.
That's true, but this here is also pretty low, right? Because you're actually saying, what's the probability of getting exactly this particular digit, right? That's actually super, super low too, right? So it's not clear which one is larger, which one is lower, right? Any more examples? Yeah?
You just have two events that can't occur together.
Perfect, exactly, right? So let's say you have two events that are both indicative, but they actually never occur together, right? So a neat example is, for example, email spam, right? So this base is used a lot for email spam, but there's different types of spam, right? They're quite distinct, right? So for example, you have Viagra spam, where people try to sell you Viagra. And there's Nigerian prince spam. I don't know if you know Nigerian prince spam. It's like, someone's like, I'm from Nigeria, you know, and I have $30,000 that I really want to give you, right? Because I'm from Nigeria. And so please, I just can't afford the transaction fee because I don't know why. I have $30,000, but the story doesn't really add up. So why don't you give me $200 and then I will give you $30,000, right? And surprisingly, many people end up doing this. But these are very different spammers, right? So these are totally different people. They have, they have nothing in common. So both of them, you have the word Nigeria in your email. It's pretty indicative that it's spam. If you have the word Viagra, it's pretty indicative that it's spam, right? So both of these words are pretty, likely given that it's spam. But seeing both of them together is extremely unlikely, right? There's actually so far there's not yet been anyone who's like Nigeria and trying to sell spam and also wants to give you $30,000, right? That's so if you actually write an email, maybe you talk about spam emails, right? Something that I could send out to you, and I mention both of these words. Actually, that's actually, given that it's spam, seeing both words is really unlikely, right? It's actually very, very small. But if I decompose it and I say, what's the probability, given that it's spam, that I see Nigeria, and what's the probability that I see Viagra, it's actually pretty high, right? So in this case, actually, I'm overestimating, right? Very nice example. All right, good. So what I want to do today, in the last couple of minutes, is start looking into a few cases of naive Bayes. So just to make this a little bit more practical, and to show you how it's actually used in practice. Okay, so what we said is we have this distribution P, let me just erase it, P of x given y, and this is ultimately what we're approximating. So that, so far so good, that's the first assumption we've made. We have to make a second assumption, and that's what that distribution actually is, right? And so early on, when we talked about MLE, we talked about the binomial distribution, but we could actually talk about many different distributions, it could come up in practice. And so let me go over a couple. Let me just see, what's the first one? Do my notes. Oh yeah, so the first one actually that's the easiest one. So if we actually say, what if my data has categorical features, right? So basically I have a feature vector x, and each x alpha is element of some set, of 1 to k, right? So my x is element of r to the d, but each dimension can only take on one of k values. So for example, a typical example would be, patient data in a hospital, right? And so for example, the first feature may be, are you male or female, right? That's then, k equals 2. Then another one could be, what's your marital status, right? And so on. So these are kind of typical questions they ask you. Are you allergic to anything? And they give you basically a couple of things to choose from, right? And that's basically all you have, right? Or similar, actually the example we just had was, do you wear a cape, yes or no, right? And so in this case, this is exactly the thing we talked about in the previous, in the MLE lecture, like a few lectures ago, where you basically say, well, the probability of a certain feature, having a value j given a certain label is estimated as some parameter. That's basically, we had earlier, that's our theta, that was the theta of our coin, and we call this indexed by the dimension and basically actually by the feature value and by the class probability. And these are normalized. Let me explain this in a second just to make sure everybody's with me. So what let me just explain what I mean by this. So this is actually really, really simple. What I'm saying, for each feature, basically, I take on one of these k values. So in some sense, I'm rolling a die with k faces, and I have some probability for each one of them to come up, right? And so overall, they have to sum up to 1. Right? So if I sum over J, which is basically the feature type, this should sum up to 1. And I have a different die for each class and for each dimension. Okay, does that make sense? So for each dimension, that's basically the question I'm asking, the feature I'm asking, are you male, female, for example? That may just be a coin toss, right? It's a male, that comes up with either male or female, right? But it may not be 50-50. For example, in hospitals, actually, because men die earlier and women live longer, but you're actually mostly in a hospital when you're old, right? It could be the distribution is more shifted towards women versus men or something, right? But basically for each feature, for each label, you have a different die, and the probability of the size of the die have to sum up to 1. Raise your hand if that makes sense. Okay. So then the question is, how do I estimate this? And this is exactly the MLE or map approach. So I basically say the probability that given that I have class C, and this notation is horrible. I apologize. I hate this notation. Now that I'm seeing it, it's awful. All right. So the probability of xj equals j given y equals c, which is my theta jc. Wait, where's my alpha? The x alpha here equals, and basically what I'm doing is I just go over all my data points, and I say how many times do I observe this particular label, and how many times do I also observe this particular feature value, and then I sum over the total times I observe the label. Right, and I can do smoothing if I want to. So I can do plus L times K alpha, which is this is just how many different features there are. So this is actually nothing new. This is exactly the same thing what we did last time with MLE and MAP. Raise your hand if that makes sense. Okay, awesome. So let's get to the more interesting part. So the only thing that's maybe confusing is because of the thetas, but otherwise it shouldn't be any surprises. Okay, next thing is, what if we don't actually use a binomial distribution? What if we use a multinomial distribution? That's something you have not seen yet. Multinomial distribution. Okay, so binomial distribution, we said each feature can take on one of k values. And basically what we're doing is we're rolling a die that has k different numbers on it or something, and they have different probability, and then that's basically how you assign the feature value. And we're trying to estimate that die. Multinomial distribution, the process is a little different. And that's typically used, for example, for spam filtering, actually. So most spam filters that you use on your whatever MacBooks or something actually just use a naive-based classifier with multinomial distribution. And so here's the idea. We draw m words, right? So you have an email. The email has m words. And the way it works is you basically draw repeatedly without replacement. So, with replacement. So you have a distribution of all possible words. So there's some probability that you draw the word the, some probability that you draw the word a or something, right? And then what you do is you basically just, from this distribution, you just draw m words, and that's your email. Okay? The key insight is that you have different distributions for different labels. So you assume that spam emails are drawn from some distribution, where, for example, the word Viagra and Nigeria are now disproportionately more likely, and not spam emails have a different distribution. So in my case, for example, the word Kilian, right, is pretty likely if it's not spam emails, because a lot of people send me email addressing, obviously addressed to my name, right? So, and what these spam filters are basically doing is they just estimate these probabilities from the data. Let me formalize this. So basically what we're saying is each feature alpha can be can be up to m numbers. And m is the 1 to d. And this here is no longer a feature, this is a feature value, but actually it means something specific. This actually means how many times this particular word is present in your email. Okay? So your feature vector here is actually not, it does not have as many dimensions as you have words in the email. It has as many dimensions as you have words in the vocabulary. Right? So in the English language, there may be 10 million. Right? So you have a really, really large dimensional vector. And what you're doing is for each one of these dimensions basically represents a particular word. Right? So let's say x1 is the word the. Right? And then you count how many times do I have the word the in my email. Okay, that may be 5. Right? So then the first entry is 5, right? That corresponds, well, it's, let's say the word a, right? That's alphabetical order. The second one may be the word and, right? How many times do you have the word and in your email? Well, probably not, actually, right? And so on. Then you have the word all, right? And all, well, how many times do you have also 0, and so on. And so you count, you basically have counts of how many times each one of these words is in your email. And the total sum of all these counts is exactly m, which is the number of words that you have in your email. Raise your hand if that makes sense. All right, awesome. So, of course, in practice, you don't store all these zeros, right? So that's the trick, right? Otherwise, it would be extremely inefficient. So the question is, what is now the probability of a certain vector x, given that I have, a specific number of words, and that my email, that I know the label, right? So it's either spam or it's not spam. And, well, what I'm doing is I basically, again, have a probability that I'm assigning to each word. And so here's what I'm doing. I basically say, okay, well, the first thing is the order of the words doesn't matter. So what I'm doing is I say for each one of these times xd, this is how many combinations I could rearrange my words in my email, right? I could have all the a at the beginning and so on. And I could rearrange the words in my email alphabetically and would give exactly the same representation, right? So this is good old probability theory that you've learned in middle school or something, right? So this is just basically, considering that there's many different ways of reordering the email, which don't actually make any difference. And then you say, okay, well, I'm going now I'm going through my email 1 to D. I look at every single word, and what's the probability that I'm drawing exactly xd of that particular word. So theta alpha c here is the parameter that basically says that given that the class is C, given that it's spam or not spam, what's the probability of drawing word alpha? And I drew it exactly that many times. This should be an alpha, sorry. Yeah, this should be an alpha, right? So I drew it that many times. Okay, does that make sense? So this here is basically the probability of coming up heads or whatever, right? But that is the probability of that word. And I came up that many times. So this will be the probability of receiving exactly the email that you observed in that order. And if I multiply with this term, then I say, well, if I reshuffle the words, it doesn't make any difference. Any questions? Raise your hand if that makes sense. Raise your hand if you want to go outside and be in the nice sunny weather. All right, good. See you all on Monday.